going to look at what happens when you want to quantitatively talk about the change in an equilibrium system. So even when you do this lab this afternoon, you're going to qualitatively figure it out. Is it yellow? Is it orange? And sometimes, as you know, seeing colors is not always so straightforward. So qualitative analysis has a limited amount of usefulness, really. So quantitative is usually what we try to move towards, okay? So we're going to look at how we can talk about changes in an equilibrium system using math. So after this lesson, so this is a beefy lesson, you can already calculate the equilibrium constant, but we're going to look at a different way to do that as well, like different ways to get those values. You're going to be able to calculate equilibrium concentrations of a substance when you know the KEQ as well as other concentrations. You're going to be able to, after we do problem number 4, figure out, based on the math, is the system at equilibrium or is it favoring the right or left side? Again, based on the numbers. And you're going to calculate equilibrium concentrations when you have initial concentrations and you know the equilibrium constant. Okay, so a lot's going on here. So when we look at, again, we're going to do concentrations. We're going to make an ICE table. So in the Le Chatelier note, it did talk about what are the initial conditions. So we're going to use the acronym ICE, I for initial. Again, when we make an ICE table, you're only going to use concentrations. So that square brackets, again, is a universally used short form for concentration. Then we're going to look at what is it changing by? What is the change in concentration, or C? And then what is the concentration at equilibrium? And you always have to have concentrations in an ICE table. So if you forget how to calculate that and you want to add this in as well, C is N over V, moles per liter. And it's kind of one of those things. Sometimes if I want to get like an extra mark, I'll make you calculate the concentrations first. Sometimes you're given concentration already. It just kind of depends. Just read the question carefully. If you're given moles and you're given liters, then make sure you calculate concentration. So what we're going to use the ICE table for is we are going to build our own expressions to help us solve. So do we have to solve for KEQ? Do we have to solve for equilibrium concentrations? What are we doing? Okay. So usually it's easy to know as a scientist what is the initial concentration. Sometimes it's easy to figure out what's the final concentration or what after equilibrium is established. What is this? But you can also, using stoichiometry and mole ratios, figure out if you have certain initial conditions, how would the equilibrium change, and then what would the new concentration be. So just like we did with Le Chatelier, where we said it would shift to the right, whatever the product was, that would increase the concentration, you can do that here, but now you can also do it with actual numbers. And that's what we're going to do. So we're going to build our own expressions. So when you have an ICE table, the big thing is that it's like you've got initial conditions, then something is changed, and then you get a new concentration at equilibrium. I'll make that bigger. So initial, then the factor it's changing by equals what's at equilibrium. So we are going to build our own expressions with x's because we don't know what it's changing by. So this really is, you kind of have to think about algebra and grade 9 math and stuff like that. Okay, so, and we're going to use the quadratic formula. So this is really where, again, sort of similar to last year, we kind of build towards the quantitative side of chemistry. Okay, so problem number 1. So these are, instead of calling them examples, I call them problems for whatever reason, but the idea is that each of these problems is a little bit different. So the questions that are listed for the homework are specific to that type of problem, okay? So just doing these, for example, is not good enough, okay? If you really want to do as much as possible, you have to take a look at each of the problems. So one of the problems with these problems is trying to decide what to do, okay? So you really need to read the question carefully. So it says when 1 mole of NH3 gas and 0.4 moles of N2 gas are placed in a 5-liter container. So first of all, you're given moles and then you're given a separate liter. Is that concentration yet? No. So we're going to calculate 1, 2, 3 concentrations. So that is like 3 marks, okay? So that concentration moles per liter thing is important. So 1 mole of NH3 gas and 0.4 moles of N2 gas are placed in a 5-liter container and allowed to reach equilibrium. So they're initially placed in the container, then they reach equilibrium. At a certain temperature, and somebody asked me this yesterday, sometimes they just put temperature in the question as a way to standardize it because now you know temperature can shift the equilibrium. So what this is saying is at a certain temperature, these are what the concentrations were. If it was a different temperature, it would be different, but we're not worried about that. Okay, so if it gives a temperature value, which I think it does in 2 and 3, we actually don't even need that information. Okay, it is found. Okay, so allowed to reach equilibrium, it is found that 0.78 moles of NH3 is present. So initially we put some in, then it reached equilibrium, and the equilibrium concentration was calculated. Okay, so we have I and we have E. Okay, so you have to be given the reaction, and of course you want to make sure this is gas, 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 right? It has to be gas or aqueous. So we're going to find the concentration of each substance or species at equilibrium. We're going to switch that back into moles. You don't always have to do that, just kind of read the question. We're going to calculate the KEQ using our concentrations. So in this problem, we're given one of the amounts at equilibrium, but there is no equilibrium constant given, no KEQ value. So that is the main difference between problem 1 and problem 2 and 3. So before I do anything from the grade 12 part to this, you have to have concentrations in your ICE table. So you will get 3 marks, like I said, for changing the 1 mole, the 0.4 moles, and the 0.78 moles into concentration. So these questions are beefy. So, they'd be like at a 7 or 8 or 9. So there obviously can't be like 10 of these on a test or exam or whatever, right? Even in normal situations. Okay, so let's find concentrations first. So also, if you want to make a note for yourself, that chemists are lazy. Remember, moles per liter can be changed to big M, okay? Instead of having to write moles per liter every time. Also, the big M comes from, we often say, 0.2 molar, or the molarity. If you want to write moles per liter, that's totally fine. When you are proficient with this and you've done a bunch of these, if you just want to write these numbers in your ICE table, like you don't even show this calculation, that's fine too. Okay, so we're going to build our ICE table. And I recommend that you sort of think of it literally like a table, where you have a column, 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 okay? So I, initial, change, and what's at equilibrium? Okay, so we just calculated the initial condition of NH3 was 0.2. So again, when you're doing these questions, if you don't show that other step, if you just write the 0.2 right in here, that's fine. Just make sure that you put concentrations in the ICE table, not moles, okay? And then we were also given 0.08 molar N2. And then when you're not told anything about the other reactant or product, you can just put 0. So this question, I tried to combine everything-ish. So normally 97% of the time, you're going to be given the initial condition of the reactants and both products will be 0, which makes sense. You initially put some reactants in and then the products, you don't put products in, right? However, sometimes you can put products in and then it would go in the other direction, but that's like reasonably tricky, okay? Normally, both products would be 0, so this one here is 0. So then you have to think about what is the equilibrium going to do? Now in this case, we're given NH3 at equilibrium, so it started at 0.2 and it changed to 0.156. So did it go up or down? Down, right? Which makes sense. Reactants get used up. But there are going to be cases, like in problem 2 and problem 3, where we're not given something at equilibrium. So you can think of it lots of ways. If there is none of this, 0, can you go down from 0? Can you have negative concentration? No. So then it can't go this way because there's none of this to use. You could also think of it like if there is 0 of this, then there's more of this side, so it has to make more of this. You can think of it that way too. But the math is logical every single time, because what we're going to do, we're going to figure out how much it's changing by, and it either has to increase, which is positive, or it has to decrease or be subtracted, which is negative. So if you put a negative number here, 0 minus a negative, you can't do that. That doesn't make any sense, okay? So in math or whatever, when you're analyzing something, if you don't know what it is, what's the most common variable to use? X. So we're going to use that here. We know what the initial condition was. We know what the final concentration was. Do we know the number, the actual amount it changed by? No. Can we solve for it? Yes. So we're going to be solving for X. So that's what our substances are going to change by. So X, X, X. However, when you have coefficients, and we talked about this in the rates unit, they're not all going to have the same rate. We have to take into account the coefficients. So this is 2x because of the 2. This is 3x because of the 3. This is x because it's only got a coefficient of 1. So that's why I've highlighted these coefficients here. It's going to affect how much it's changing by. So yes, it's moles. Yes, it's all going to change by a similar factor, but you have to take into account stoichiometry. So this change line has lots going on with it. So you have to think about, is it going to be positive or negative? Is it going to go up or down? And does it have a coefficient? Okay? Oops. Sorry. I just have to fix my chart. So I even made these colorful. Change is negative, that's yellow. Red is positive, it's plus. If you like color, you can do that. You don't have to. Okay, so we've decided that it's going to shift to the right, so these are going to increase. Again, you can't, if you made this negative, you do 0 minus negative 3x. That makes no sense, okay? You can't go down from 0. So wherever the 0 is, and this is going to be true all through this section, all through solubility, all through acid and bases, wherever the 0 is, that's where the positive x should go, okay? And just take into account the coefficient as well, okay? So now we need to build the equilibrium line. So whether you have a problem like this or a problem like problem number 2 and 3, where you're not given something at equilibrium, you still want to build your expression. So I plus C equals E. We're still doing that. So we have 0.2. Now, the reason we write plus, it does have to do with the math. If you do 0.2 plus negative 0.2, what does that change into? 0.2 minus, right? So leaving it as a plus, even though some of them will be negative, will make the math work out. You can write it like this, 0.2 plus negative 0.2x. You can write it like that. It doesn't matter. The math is the same, okay? So you have to do I plus C equals E. So we have the ammonia started at 0.2. It went down by 2x, so minus 2x. And then in this question, we are given ammonia at equilibrium, 0.156. Okay? So I plus E, I plus C equals E. Yes. Yes. And that has to do with stoichiometry, right? So then, but we take into account the coefficients as well. So now we don't know anything else at equilibrium. So all we can write is I plus C. So here, I'm going to write the 0 plus 3x. 0 plus 3x is just 3x. So again, once you do a bunch of these questions, you might want to just get rid of that. That's fine. Or you can write it out every time. So all we can write in the E line is 0 plus 3x. We don't know, without doing calculations, its concentration at equilibrium. We were not given that, only ammonia. And then for the nitrogen, 0.08 plus x. Again, we don't know anything about it at equilibrium without doing some calculations. So now we have 3 expressions, 1, 2, 3. Yes, the x, it's going to change by a similar factor. However, we have to take into account what it started at initially, 0.20 and 0.08. And we also take into account the coefficients and whether it's going to go down, because it's shifting to the right, to make more of this, or if it's going up. Okay? So when you have, when you know one of the concentrations at equilibrium, you can easily solve for x. You decide for yourself how much grade 9 math you need to show, okay? So you have to collect like terms, bring the number to the other side. And if you don't want it, if it screws you up, you don't have to include the units here, okay? And again, you could do this in your calculator. You don't need to show that extra step, but I will. Oops. So now we have negative 2x. You need to divide by negative 2. We don't want the x value to be negative. Again, you can't have negative concentration. That doesn't make any sense. That's not possible. So we get 0.022. Okay, so I'm going to scooch back to here for a second. So now we have x, but if you go back and look at the equilibrium line, are any of these values just x? No, okay? So please don't find x and think, oh, I'm done, that's it. Never. That's never going to happen, okay? So you are never done once you find x. This is not going to answer the question. Whether you have to find the concentration or the moles or the KQ like we do in this problem, or just one of them, you are never going to be done once you solve for x. So now you have a choice. So again, some people will they'll leave space under their ICE table and sort of go and plug it back into each column. That's fine, you can do that. If you printed the note off, there is a spot. So the next slide says, like, we're going to finally answer A. So if you want to keep with the, like with the boxes, then you can do that here. Yes. So wherever the 0 is, it has to make some of that. So those ones are going to increase, and the side that has no zeros will decrease. You're basically shifting to make more. Like if you don't have any, then you have to go to the side that makes some. So those concentrations are going to go up. The side of the equation that doesn't have any zeros, you're going to shift away from that, or like those ones are going to go down. They're going to decrease. They're going to get used up. So they're subtract or minus, negative. Okay, so we're going to sub the x back in. So you always go back to the equilibrium line. So like I said, some people prefer to just write it underneath their ice table. But in this case, if you printed the notes off, you might as well put it in the box there. So again, I kept the 0. Obviously, the 0 doesn't change it. So as you get used to these, you might not do that anymore. So we want to solve for what the concentration is. So you want to have units, whether it's moles per liter or big M, that's fine. And check your logic. It went up from 0 because we shifted right. Yes, it did. Same thing with the other one. It has to increase from 0.08. Okay, so B says to find the moles. So we're going to change it back into moles. You don't always have to do this, but just in case you do, I'm just going to show you. So instead of doing, so if C is N over V, then moles is C times V. Sometimes it's actually, it'll say moles, like what's the answer, like how many moles at equilibrium. Often the volume is 1, so then it's the same, and it's like, seriously, but just so you know, but this case, it happens to be 5 liters. So what are the number of moles? It only says N2 and H2, so that's, you don't need to change the other one. Okay, and then it says, what is the value of KEQ? So you get marks for writing out the equilibrium law. Okay, every single time you have to, you have to write this. The products over the reactants raised to the exponent, you have to show that. You have to. If you, you know what? You don't have to, but then you're going to lose a mark, okay? So unlike yesterday where it said write the equilibrium law, in this case, hopefully by now, like if, again, this was normal, this would take a little bit more time, but you would just be used to doing it. You still get marks for it. You still have to do it. Okay, so let's talk a little bit about problem number 2. So problem number 2 is different. So this time we are given, it says the equilibrium constant for the reaction is 50. Again, it's giving you the 448 degrees Celsius because if it wasn't 448 degrees Celsius, it would not be 50. So it's just kind of a way to standardize the question. We actually don't need that. So we have the equation. Hydrogen gas, iodine gas makes hydrogen iodide. All gases, so that's good. And it says find the equilibrium concentration of all species when 1 mole of H2 is mixed with 1 mole of I2 in a 0.5 liter container and allowed to react. So this time we are not given anything at equilibrium. Problem 2 and problem 3 are different because in this case these are both the same, 1 and 1. Their coefficients are the same, 1 and 1. So that's going to make the question a little bit easier. Okay? Problem 3, we're going to have to use the quadratic formula. Now, this question, you can also use the quadratic formula, but there is a shortcut if you can see it. If this type of problem you want to use the quadratic formula every single time, it's totally up to you. Okay? And then, again, we're going to change it back into moles. Oops. So this time we can't calculate KEQ because this time we're given it. Okay? So we're still going to do the same thing. 1 mole and 0.5 liters. We have to find concentration first. Okay, so the only concentrations we are given are the initial. So 1 mole divided by 0.5 liters makes 2 molar. So what I'm going to do is write a bunch of notes. You decide how much you would like to have in your note about what's going on here. So this time we are not given any equilibrium concentrations, so we have more work to do to solve for x. We need to write the equilibrium law, which you get marks for, and the KEQ value to solve for x. So in this case, you don't have to use a quadratic formula, but you might have to. So some students just prefer to do it always. And the big thing with the equilibrium law, you have to put the equilibrium line from the ICE table in there. So you have the equation, and this time, this is the KEQ value is 50. So it asks us to find the equilibrium concentrations. So when we're going to find the equilibrium concentrations, we have to use an ICE table. E stands for equilibrium. And decide how you want to make your equilibrium arrow. You can draw it like the PowerPoint makes me do, whatever. You can draw the double-sided arrow. It just has to show reversibility somehow, okay? So we're going to do ICE. And we already calculated the concentration, which was 2. Okay, so this is most of what the questions would look like. You're given information about what hydrogen and iodine, which are the reactants, what they are initially, and then you're not told anything about the product. But it makes sense that you don't have any product to start with, so it's 0. Right? This is most reactions. You start with reactants, you put them in, and you make some product, right? Okay, so now we have to do the change. So these two have a coefficient of 1. This one has a coefficient of 2. So you have to put the 2. So if you want to highlight that for yourself or whatever, make it apparent. Okay? And now you need to decide which one's going to increase and which one's going to decrease. So again, can you go 0 minus 2x? No, you can't go down from 0. It has to shift to the right in order to make some hydrogen iodide because there isn't any. So this one has to increase and these two have to decrease. And we're going to write our own little expressions. I plus C equals E. But this time, we don't know anything at equilibrium. So none of them can be solved just by simply rearranging and solving for x. So here we have 2 minus x, 2 minus x. And here we have 0 plus 2x. So you decide, do you want to write 0 plus 2x or just 2x? Okay? Doesn't matter. All right. So we don't know anything at equilibrium. That means we have to know something else. So what do we know this time? We know KEQ equals 50. That's in the question. So we're going to use the equilibrium law and the KEQ value and solve for x. So if you wrote down all the notes previous, it talked about having to do more work to solve for x. We're going to use the equilibrium law, which you get marks for. So check, gas, gas, gas. All of them are included in the law. Exponents become, or the coefficients become the exponents. Products over reactants. So the same principles that we talked about yesterday. So you would get a mark for this. Don't just write P over R. Don't write nothing. You need to write this out if you want full marks, okay? So we're going to use the equilibrium law. We're going to use the KEQ value. So logically, if this is KEQ, then we're going to use the equilibrium line, not the initial, okay? We don't know what it is at equilibrium. That's the whole point. That's what A says. Find the equilibrium concentrations. So we have 50. We have 2x squared. And then in the bottom, we have 2 minus x and 2 minus x. So what you're going to focus on this year is equations that, if you have to solve for x like this, equations that are either linear, so the exponent on x will be 1, or equations like this, which are squared, so the exponent on x is 2, because grade 10 math, you should have used the quadratic formula. Those of you, again, that are going to continue, yes, you can have higher order equations. Now, this is really common. Sometimes students are like, Ms. Todd, how is it always going to be quadratic or linear? But remember, if you're talking about collisions, you can't have some crazy equation every single time. That's just logically not going to work. Yes, you can have more complicated equations, which would involve more complicated math. So again, if you're going to continue in pure chemistry, then you will take things like calculus and stuff like that. Obviously, that's not a requirement here, so we're going to stick to either linear or quadratic, okay? So now we have, this is a special case, problem 2. It's very similar to problem 3, except we have a squared in the top, and this is squared in the bottom. So to get rid of, or the inverse operation to squared is what? Square root. So you can square root these because you have a squared in the top and a squared in the bottom. So this is a shortcut. Once we do problem 3 and we do the quadratic formula, you could definitely use the quadratic formula here. Again, it's going to take some significant algebra to get there, but you can always, as long as it's quadratic, you can always use the quadratic formula. So, but this is just a way to kind of streamline your work. Don't forget to square root the 50. That is a very common mistake. Oops. So now, similar to the quadratic formula, because there are two answers, a positive and negative, when you square root, and when you're in grade 10 math, you kind of split it apart, we're going to do the same thing. So we're going to find two x values and decide which one makes sense. So I'm just going to write that again, okay? But you don't have to. So you can do the positive root and the negative root. And really decide for yourself how much work you need to show. We need to get the 2 minus x out of the bottom. So you have to multiply both sides by 2 minus x. Then distribute. And collect like terms. But there are definitely shortcuts you could take, okay? If you want. If you don't want to, great, show all your work. And then do the same thing over here, except now we're going to do the negative root. So if you want to like draw a line between them, So when you did quadratic equations in grade 10, sometimes it was one was positive, one was negative, and then it was obvious. Let's say you were doing parabolic motion, like dropping something from a certain height. Then one of the values would be negative, and then you can't have negative time, that kind of thing. Often, what's going to happen is these values are both going to be positive. So you just have to think for a second about which one we're going to use. We're never done once we solve for x. So we're always going to go back and then plug them in to our equilibrium line here. 2 minus x, 2 minus x, and 2x. So if you plug in 2.78 here, what would you get? A negative. Does that make sense? No, you can't do that. So we call that inadmissible. You could just cross it out if you wanted to. So this is the x value we're going to use. We haven't even solved yet, right? We're not even done A. So these two are the same. You could do them separately or you could do them together. That doesn't matter. Both of them, we're going back to the ice table. So like I said, some people will like to do this right underneath, which if you have room, that's fine. So they'll do it right here. Just make sure that you have units, okay? Or you can write it out separately. Okay, so either big M or moles per liter, whatever you like better. It says to do everything this time, so we have to do HI as well, which makes sense because we didn't know anything at equilibrium, right? So we have to solve for all of them. Again, you don't always have to go back to moles, but B says change H2 and I2 back into moles, like how many moles are left. I'm going to put more than one equal sign on a line. I apologize. So we have the molarity. You just multiply, I think the volume is 0.5, and that's it. Okay, so problem number 3 is the same reaction. So if you want to rewrite it there. Again, it's up to you. If you have big handwriting, maybe you'll want to write this on separate paper. Maybe not. So the same reaction as above. So we've already checked it's all gases. We're good. How many moles of HI, H2, and I2 are present at equilibrium? So again, it's giving us moles and asking us for moles, but that's, read the question carefully. But this time it's 2 moles of H2 and 1 mole of I2, so they're not the same. So unfortunately, we're not going to get a squared in the top and a squared in the bottom, so you do have to square root. I mean, you have to use the quadratic formula. You can't square root. So get some part marks. I haven't even thought about what a nice table should look like. I just did this. So again, similar question, except now we have 4 molar hydrogen, 2 molar iodide, or iodine gas, which are not the same. So still the product is 0. It's going to increase by 2x. These two are going to go down because they're reactants. They just go down by x because their coefficient is 1. And we do the same thing. I plus C equals E. But we don't know anything at equilibrium. It does say KEQ is 50. So we're going to use that number again. We're going to write out the equilibrium law again to get full marks. We're going to fill it in. Okay, so the hallmark of math, right? What you do to one thing, you do to the other. So yes, there's a squared in the top, but there is not a squared in the bottom. So we can't just square root both sides. So now we are going to have to use the quadratic formula. So the quadratic formula is useful, however, it has to be in standard form, right? It has to be ax squared plus bx plus c equals 0. This is not even close to that, right? So we have to do a little bit of algebra. We have to FOIL, okay, stuff like that, you know, collect like terms and all kinds of stuff. So if you struggle with that or that's not your forte, then show as much work as possible because it's really easy to make algebra errors and that's very frustrating. Because then what happens is you use the quadratic formula and you get a negative under the square root sign and it's like, Miss Todd, I got a negative, and then I have to say, you know, go sit down, you make a mistake. It's very sad for me, okay? So do as much work as possible. Don't skip steps if this is not your, you know, bread and butter, okay? So first, just in case you forget what the quadratic formula is, if you like to write little notes for yourself, then the reason we're using this is because it's not squared in the top and the bottom. So we could have done problem 2 using the quadratic formula, but there is a way to streamline it. So if you hate the quadratic formula, take a look and see, is there a squared in the top and the bottom? And then you can just square root both sides, okay? So here in the bottom, eventually, it's up to you. You can like bring it up first or you can FOIL first. It doesn't really matter. We need to get this out of the bottom. This is dividing. We're going to multiply. It's up to you. You can do this now. Please, 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 please. Remember, this 2, this squared, is outside the brackets. You have to square the 2 and the x. Okay, so it's 4x squared. Also, what I tell my grade 10 math students, I recommend that you FOIL first and then distribute the 50. But again, you don't have to. So, and there is a way to streamline FOILing as well. I don't even teach my grade 10s that, to be honest. But by the time you get to grade 11, maybe you can see it. If not, just show all the steps. So 4 times 2 is 8. 4 times negative x, negative 4x, negative x times 2, negative 2x, negative x times negative x is positive x squared. Okay? You can simplify first if you want. I'm going to do all the collecting up here. So now you distribute the 50. So 400, 50 times 8 is 400. 50 times 6 is 300. 50 times x squared is 50x squared. And so when you do the quadratic formula, it should be equal to 0. So we have to bring that 4x over. So if this bothers you and you want to write it 46x squared minus 300x plus 400 equals 0, you can do that too, but you don't have to, okay? So the a goes with the number in front of the x squared term. The b is the number in front of the x term, okay? But you can rewrite it, yes. No. The numbers will be big. It's okay. Okay, so I'm going to make a new page. If you were the kind of person in grade 9 in grade 10 math that had to label what A was, what B was, and C was, do it, okay? Whatever is going to make you successful. So again, if you want to rewrite it, if that bothers you, that's fine. It doesn't matter. Okay, you can do that too. So if you used tricks before, use them again. The negative B is important. Make sure you keep that negative. And so now, again, you really should get to know your calculator. So there are plenty of calculators that can do the quadratic formula for you. That's actually fine. I don't care. It's not really an expectation of grade 12 chemistry that you show your work for the quadratic formula. A couple things to be careful of, that this now becomes positive 300. So if you just write positive initially, that's fine. When you square a negative number, if your calculator doesn't automatically put brackets, it'll give you that it's a negative answer, which also isn't true. That doesn't make sense. So just be careful there as well. And then sometimes what I would do, like say you're going to put this in your calculator all as one step, which is fine. Do 300 squared minus, and then put brackets, and then you can do 4 times 46 times 400. Sometimes when students do this, they forget the negative and then it will switch and stuff like that. So again, just show as much work as you need to, get to know your calculator so that you know what's what. You should get 16,400 underneath the square root sign. And now we're going to do the same thing. So we have a plus and a minus answer. And again, you can do this in your calculator all at once. You can do it separately. You can definitely round. And similar to before, this 4.65 is too big. It's going to give a negative answer. Yes. Yes, sir. So even if it doesn't work for one of them, that's it. It's done. I mean, in this case, it wouldn't work for the other one either, but yeah. So you can't have negative concentration. That does not make sense, okay? And similar to the first problem where I wrote in huge yellow writing, you're never done when you solve for x. Same thing here. Please don't stop here. In this question, we're going to find concentration and moles, which is like 6 more calculations that you could get marks for. So please don't do all this work and then forget to actually do the answer, okay? You'll be very annoyed with yourself. So again, it's up to you. I don't think I have room. Yeah, I don't have room under my ice table, so I'm going to write it at the end. So I'm just going to go in order. H2, I2, HI. I'm going to plug in the X, and I'm going to change it into moles. But this time, none of them are the same, so you have to do it 3 times. I'll write the other one up here. No. Yes. Okay, so once you've got that done, I think problem 4, if you printed the notes off, let's go back there. That's probably easiest because it is very different. Oh. What we're going to do, what we're going to calculate now is look at what happens when you're given values and you want to mathematically determine if the system is at equilibrium. So quotient is the answer for division. So we call this Q value the quotient because we're doing products divided by reactants. So if a chemical system begins with reactants only or only the products, it's obvious which way it's going to go. What happens if you're given concentrations of everything? Okay, so these questions will hopefully look a little bit unique. It's not going to say initially you have this. It's not going to say allowed to reach equilibrium. It's going to say give you values and then it will say is the system at equilibrium. So we're going to calculate this trial value. It's like somebody has taken a snapshot in time and said, what is going on at this concentration? So Q is calculated the same way as KEQ, and then you're going to compare them. You are not, no, ice, with many exclamation points. If you do ice, you are you're changing those concentrations into equilibrium. These questions want to know, at this snapshot in time, is the system at equilibrium? Okay, so when we're gonna sort of go back to thinking about what the fraction means, right? What the products over reactants mean. So if the Q is equal to KEQ, the system is at equilibrium. Okay, so this is very easy, right? So if you have a question on a test that's out of like 6 or 7, the chance of you just finding Q and saying, oh, equal at equilibrium is very slim. Okay, PS. So now if Q is greater than KQ, the system must shift to the left. So why does the system have to shift to the left? So when you have a number, right, when you have a quotient, or your answer is going to be a quotient, and you have a big number, so Q is too big compared to KQ. If you want the number to get smaller, what do you need to get bigger? The bottom, right? Once the bottom starts to get bigger, your number is going to get smaller. 1 over 4 versus 4 over 1. Okay? So if you want the reactants to get bigger or the products to get smaller, if that makes more sense to you, that's fine. Then either way, if this is getting smaller and this is getting bigger, you're shifting to the left. Okay? So I know it's not a huge spot, but try to fit this in. So you can, if you don't like alligator signs, then you can just say Q is greater than KQ, that's fine. The value of Q needs to get smaller, or the bottom of the fraction needs to get bigger. What's at the bottom? Reactants. What's not at the bottom? Products, so they are decreasing. Okay, so then the reverse is true. If Q is less than KQ, you want the number to get bigger, to become equal to KQ. So if it needs to get bigger, then the top of the fraction or the products need to increase, which is a shift to the right. Or you could think of it like you want the bottom of the fraction to get bigger. It's the same thing. I mean, to get smaller. Yes. Yes. Which we decided was open book. Yes? Okay. So for the example, which does not take as long, because are we going to do ice? No, 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 no ice. Okay. So the question will look weird. So it says 3 moles of HI, 2 moles of H2, 1.5 moles of I2. We're given an amount of everything. And it doesn't say initially they're placed in equilibrium, what's happening. Your textbook, I can't remember if they're sneaky, but I will be very specific. Is the system at equilibrium? Okay, so I'm asking you. I don't want you to do ice because that forces it to be at equilibrium. You're also going to be given the KQ value. So now you're given everything. You're given concentrations, you're given a KQ value. What am I supposed to do? You're going to find Q. So this should not be a question mark. That should be a double arrow. Sorry. Oh, yours is fixed. I just didn't fix mine. Oh, that's okay. So the same thing. You want to make sure you have concentration. But again, sometimes, like I said, they'll give you a question with moles, but then it's 1 liter, and it's like, okay, well, that's the same. So how clever. Okay, so I wrote them in order of the equation. It doesn't really matter. So now we have 2 molar hydrogen, 1.5 molar iodide, and 3 molar hydrogen iodide. So we're given everything. Okay, we don't need to find anything. So we're going to plug those values in and see what we get. See what our trial value or our Q is. Okay, so it's exactly the same as KEQ, products over reactants. The coefficient becomes the exponent. We have numbers for everything. So you plug it in. No, 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 no ice, right? Okay? And you get a number. So how do they compare? KQ is 50, Q is 3. So Q is obviously too small. Okay, so that means it needs to get bigger. So Q is too small, it needs to get bigger. So it needs to shift towards the products. The products need to increase so that the number gets bigger. which means a shift to the right. So let's say you had this question. It would say, is the system at equilibrium? You'd be given values for everything, but I even usually say the math is worth, say, 2 marks, and the explanation is worth 1, 2, 3 or something, okay? So I even try to hint even more that you need an explanation, that this Q problem looks very different.